Welcome. Let's take a look at taking the derivative of a definite integral. And in this case, the definite integral has a variable as its upper limit of integration. And so in this case, this definite integral defines a function of the variable x. Now, it happens to be the case that for this particular definite integral, we can actually evaluate that definite integral rather simply. So I'm going to do that over here on the side because then I want to make the connection between this derivative of a definite integral and the fundamental theorem of calculus. So let's go ahead and consider taking the derivative with respect to x of the integral from a to x of 2t dt. Well, that would be the derivative with respect to x of, now the antiderivative of 2t is t squared. The antiderivative of 2t is t squared because the derivative of t squared is 2t. So our antiderivative is t squared, and we're evaluating that from t equals a to t equals x. So this is going to be the derivative with respect to x, and now I'm going to substitute x for t, and if I do that I get x squared, minus, and now I'm going to substitute x for a for t, and that's going to give me an a squared. And now I want to find the derivative with respect to x. So this is the derivative with respect to x of x squared minus the derivative with respect to x of a squared. Now, a is simply a constant, so that derivative is going to be 0. A is not x, it's some number, and when I take the derivative of that number squared, I will simply get 0. The derivative with respect to x of x squared, though, that is 2x. So 2x minus 0 is 2x. So we anticipate the derivative of this definite integral to be 2x. Now let's look at the fundamental theorem of calculus. Suppose that f of x is continuous on a closed interval from a to b. Our function here is f of t and 2t, in fact, and 2t is continuous for all real numbers. So it wouldn't matter what value x took on, nor would it matter what this starting constant might be, because this function 2t is continuous everywhere. If my function f of x equals the integral from some value a to x, f of t dt, then f prime of x is equal to f of x. So let's take a closer look. My function is defined as a definite integral where the upper limit of integration is my variable. Notice that the derivative of this function, my f prime of x, which is simply the derivative of that integral, is my integrand. Notice my integrand evaluated at that upper limit of the variable x. So we end up with the derivative of this integral being simply our integrand evaluated at x. So in our example, the function, our integrand, is 2t. We have the integral going from a to x, a being a constant. So when I take this derivative, I'm going to take my integrand and evaluate it at this variable that is my upper limit of integration. So by the fundamental theorem of calculus, which I'm going to abbreviate ftc, we're going to take our function f of t, which was 2t, and evaluate it at the variable for our upper limit of integration. So the derivative here would be f of x, or 2x. Let's take a look at a second example. Notice that in this case, our integrand is cosine of t dt, and we're wishing to find the derivative of the definite integral from 2 to x cosine of t dt. So by the fundamental theorem of calculus, f of t, my integrand, is cosine of t, and so the derivative of that function that we have there is simply my function f of t evaluated at x. So in this case, I'm evaluating cosine of t at x, which would mean that this derivative would simply be cosine of x. So recall that we're evaluating f of t at x. Now let's look at something a little more complicated. In this particular instance, this integrand is rather complicated, and there's not a simple way by which we could actually find this antiderivative. Whereas in our previous two examples, where we were dealing with the function 2t as our integrand, or the function cosine of x as our integrand, we could have actually integrated those functions and then taken the derivative. However, in this particular case, that's not really an option. Fortunately, the fundamental theorem of calculus provides for us a rather simple way to find the derivative of the function represented by this integral. Recall that this integrand is our function f of t in reference to the fundamental theorem of calculus. And if we want to find the derivative of the definite integral, our capital F prime of x, all we really need to do is evaluate our integrand at this variable represented by the upper limit of integration. So this would end up being 5 times x to the 2/3 power divided by the natural log of x to the 4th plus x. Because the fundamental theorem of calculus tells us that we can evaluate the integrand at our upper limit of integration. And this is a much easier process than actually trying to integrate this definite integral and then have to find the derivative after that. Let's look at one last example. We have the derivative of the function integral from 3 to x of the quantity 1 plus 2t squared all raised to the t power. Now, we have no strategies that would help us integrate this integral, and yet we want to find the derivative. So we will be appealing to the fundamental theorem of calculus, this second part, and keep in mind that our integrand is our f of t, and if we want to evaluate the derivative of this function defined as an integral, all I really need to do is evaluate my integrand at the variable represented by this upper limit of integration. So this would be 1 plus 2x squared all raised to the x power. I hope you find this helpful.